All right, hello everyone. Thank you for joining us today on our live session. I'm going to hand this over to Chris and he can get things started and then I'll grab the first question.
Okay, welcome everyone to another live session for the online astronomy class, the MOOC, Massive Open Online Class. Hope you're enjoying that as we go along, and this is for juicing it up with some current information on astronomy, so the floor is open for your questions.
Oops, I'm sorry. I forgot to unmute the microphone. The first question today is from Richard Elkins, who's on with us live, who says that terraforming a planet seems to be a huge risk, huge consumption of resources, and probably would negatively impact scientific research. What's wrong with keeping the red planet red?
I agree. There's nothing wrong with keeping the red planet red. Yeah, terraforming is one of those dreams, almost science fictional dreams that planetary scientists and futurists have had for decades, maybe even longer. And the practicalities of it are just intimidating. There are actually no showstoppers technologically to doing it. It's just a massive undertaking that would cost a lot of money, would take a long time. It essentially has three stages. The first is to raise the temperature, we're talking about Mars now, is to raise the temperature of Mars sufficient to melt some of the extensive subsurface ice and essentially generate a liquid layer on the surface of the planet as it had several billion years ago. So that involves raising the temperature by 10 or 15 degrees C. And the way to do that, I mean, is basically a large amount of energy deposition. You can either import carbon dioxide in, pressurized liquefied form, or you can add energy to the surface, and people have thought of nuclear explosions for that, which is a very ungreen way of doing it. But anyway, the goal there is to essentially generate carbon dioxide into the atmosphere, which will create a greenhouse effect. And of course, that will build on itself in an accelerating way. So once you raise the temperature a little bit and start liberating the frozen carbon dioxide, and which will generate a greenhouse effect, and some of the liquid water as liquid, you serve two goals. You've increased the temperature of the planet, and you've generated a first liquid surface. The second stage involves seeding life into that liquid surface. Now, it's still going to be an extreme environment, so these are extremophiles, and we pretty much know how to engineer or find natural extremophiles that could handle this slightly modified Martian surface. The final stage, of course, having given life a grip on the red planet, is to put in oxygen-producing microbes that would generate an oxygen-rich atmosphere. You need the buffer gas of nitrogen as we have in our atmosphere, maybe not at the same percentage, but making a truly Earth-like breathable atmosphere is a massive undertaking, and it will take centuries, if not a millennium or so, and cost many, many, many trillions of dollars. So most people think it's a completely infeasible thing to do. It actually is far cheaper in the end to take care of the Earth and make sure we can live on it, and if we, of course, eventually have to go into habitats within the Earth or into bubble domes because our environment and air has been contaminated, that would be little different than living in such bubble domes on Mars, except Mars is much further away, much more expensive to get to. So yes, terraforming is a vision that's really beyond reach and probably should stay that way.
The next question is from viewer Jammy Pants, who has a question about main sequence star chemistry. If iron is the final core element to remain at the end of a star's life, is the majority of the nova ejecta iron as a result?
If a star is of the kind that will produce a nova episode, which is a recurring explosion, actually slightly more massive than the sun to get that stage. It isn't majority of iron because when a star generates its heavy elements, it does it in a sort of onion skin fashion because the higher temperatures generating the heavier elements are closer to the center of the star. Now, there is some mixing of this material because there's radiation carrying energy out from the center of a star and also convection. The convective zone is a little further out, though, And so it doesn't efficiently mix the heaviest elements that are produced in the center of the star. So when the envelope of the star is ejected, which is what will happen in a nova or a planetary nebula equally in the same sort of mechanism, that material is enriched with heavy elements, but actually only a fraction of the heavy elements that are produced in the center of the star. So it's just mild, very small amounts of iron and nickel and those heavier elements.
All right, thank you, Chris. The next question is from Junaid Atta, who would like to know if there are any possibility for fast radio bursts in the Milky Way galaxy, and if not, then why not?
Yes, I mean, the phenomena that lead to fast radio bursts, it is a possible phenomenon for the Milky Way. These are energetic phenomena, sort of cataclysmic phenomena in the late stages of a massive star, sort of hyperstar, if you like. And these are just very rare events statistically and in temporal terms. And so the odds are essentially against seeing a fast radio burst in our galaxy. Once you can sample, because they're so energetic and visible over very large cosmic distances, the odds are much greater that you'll see one of these events in an external galaxy or a distant galaxy. Sort of the same with supernovae. Supernovae are rare energetic events that do occur in our galaxy about once every 50 to 100 years on average. But if you want to see these events, you're better off looking in nearby galaxies where you can look at enough galaxies that one will be happening at any given time you're observing, or certainly within a month or a year.
The next question is from Tim, who is on with us live, who says, the day the space industry reaches the level when it's time to mine and harvest resources like planets and asteroids, what do you think the political impact would be? For example, how do you claim something in space?
Actually, it's very easy to claim something in space because there are no laws that govern property, ownership of property in space. Space law is, in treaty form, is really governed only by 2 treaties that have ever been signed through the United Nations by a significant number of countries. One was the Outer Space Treaty of 1964, I think, or 65, and that was very important because that essentially banned weapons in space, tried to de-weaponize space. And then there's the Moon Treaty of 1979, which dealt a little bit more with property rights and ownership, but it was ironically not signed by most of the world's countries. And the truth is that once you get to other objects like Mars or asteroids or other places where there might be resources, there are no rules. Nobody essentially owns these. And so sort of it's first come, first serve. The people who declare ownership of them, probably that's de facto, they will have defensible rights. And so they will essentially own the mineral properties. Now, the cost of mining asteroids for resources is phenomenal. So the investment required is phenomenal, and the return is fairly uncertain. So maybe we shouldn't begrudge someone laying claim to a near-Earth asteroid that they think has rare earths or metals sufficient to make a lot of money, because the most likely outcome is that they're going to lose their shirts. People have worried about imposing some layer of regulatory process on space, property in space, objects in space, but the United Nations nor the world superpowers have shown very little interest in doing so. So it essentially isn't going to happen anytime soon.
All right, the next question from one of our live viewers is from Karen, who would like to know if you believe that liquid ammonia could be a viable option for a substitute for water for other life forms.
It's an interesting question. So biochemists or people who work on extremophiles or extreme forms of life have definitely speculated that water is not the only possible liquid medium for life to exist. Now, biologists, astrobiologists contend that life does need a liquid medium, because a liquid solvent, especially a solvent that allows chemicals to dissolve and then combine within that medium, that provides an opportunity for growth of complexity as simpler things come together and attach and form more complex molecules. So you do tend to need a liquid medium for life. It's very unlikely that life could form within a gas, for example, or a solid, because there's no mobility at all. Does it have to be water? Not necessarily. Water's a good a prime ingredient because it's abundant in the universe. It's one of the most common molecules in the universe anywhere. And in terrestrial planetary environments, it's going to be fairly abundant. Ammonia is less abundant, but obviously we can see ammonia in small components in Titan. So Titan has oceans and lakes made of ethane and methane with a little bit of water and a little bit of ammonia. So ammonia does have some properties. It tends to dissolve things, and so does water. So in a sense, there's a simple trade-off. They're both about equally good or bad as far as combining and forming complexity. Another ethyl alcohol is another possibility. So people have come up with various other molecules. They're all, however, less abundant than water. And so in the end, water is the most likely medium for life universally.
Thank you, Chris. The next question is from Byron, who's on with us live, who would like to know how far off is our technology in terms of being able to deduce that an exoplanet is, like our Earth, surrounded by orbiting artificial satellites.
So inspecting exoplanets at that level, at the level of looking at their environments, is far off, actually. The resolution required of a telescope, so say the nearest Earth-like exoplanet is the nearest conceivable distance is Proxima Centauri systems. That's 4 light years. 4 light years is a couple of tens of trillions of miles away. So the idea of looking for something that's truly tiny, a satellite that's meters across, even if it does reflect some light from the nearby star, is very low. You could just do the thought experiment of how far away could we go from the Earth and be able to see by reflected light gathered by a telescope the satellites around the Earth, and the answer is not very far out in the solar system. So by the time you've gone to a nearby solar system, which is hundreds of thousands of times further away than the planets are in our solar system from each other, your odds of detecting that kind of technology are minimal. The frontier for exoplanet characterization would, for example, be the detection of oceans and continents on the surface, where if you had spectroscopy, you could probably detect the water in the oceans, and you might even detect the chlorophyll edge on vegetation on the land. So that's the limit of resolution, and even that can't be achieved now, but that's within maybe 10 years. We might actually be able to look at continental masses on the nearest exo-Earths.
Excellent. Thanks again, Chris. So the next question is from Benjamin Hippler, who would like to know what level of indirect evidence for alien life do we need to be able to say we are not alone?
I think the indirect evidence won't cut it. Carl Sagan had a famous quote on this topic, which is extraordinary claims require extraordinary evidence. And the claim of life beyond Earth, especially intelligent life beyond Earth, is an extraordinary claim. Not that it's a priori low probability or impossible. It's just that the stakes are obviously incredibly high on contending that we found something like that. So the evidence is going to have to be good, which means not indirect. Now, indirect evidence in the world of UFO sightings, of course, tends to revolve around eyewitness testimony. Eyewitnesses are notoriously unreliable, and that's just setting aside whether they have any self-interest in, claiming to see something they never saw. There's photographic or imagery evidence, and photographs were easy to manipulate before digital imagery. Since digital imagery with CCDs, photographs are incredibly easy to manipulate and easy to cover your tracks and make it very hard for anyone else to tell you faked the image. So that kind of evidence of extraterrestrial life in any form is simply not going to be convincing. Probably the only evidence that's going to be convincing is the kind of evidence that SETI is looking for, which is an artificial and imputed intelligent signal coming by radio waves or pulse laser or some other method, some other technology from a distant Earth and collected by a telescope. So if this signal was seen by professional astronomers doing the SETI activity and verified, that would be pretty convincing evidence. The other type of evidence that might convince most scientists, even the ones being suitably skeptical, as Sagan admonished, would be physical evidence, an artifact essentially. Maybe an artifact left behind by an alien visitation to the Earth, as many people speculate. It's almost a conspiracy theory to say that. But if there were an artifact that turned up that, when scrutinized in the lab, atom by atom, really showed that it couldn't have been produced by our technology, that would be pretty interesting and compelling evidence. Equally, we might look for artifacts in the solar system. Arthur C. Clarke, of course, worked this into some of his science fiction, and it's been part of other science fiction writers' idea toolkit as well. So looking for artifacts in the solar system or beyond, or sentient probes that are watching us and understanding that they weren't produced by us and must have been by an intelligent civilization. These are things that would be pretty hard to refute. And people are, of course, looking for these at a low level. It doesn't take a huge amount of astronomers' time to do this, but there are a few projects. And so if that evidence came up, it would be heavily scrutinized. Skepticism is always the starting point for astronomy. Excuse me, let me kill my phone. Okay, sorry, ready for the next question.
All right, thank you, Chris. So the next question is from Jean Doe, who's on with us live, who asks, if there are colors and matter that we can't see, like infrared and dark matter, is it possible that there's other stuff in space that we can't see or detect that might have very different physics? Like, would it be possible for a planet that looks dead to be very much alive with life we can't see or detect in some way?
So things that are hard to detect or see, they're intriguing, certainly. And we're talking well beyond dark things, that is to say, things that don't reflect light. So obviously, there are things that are dark, and if we're using visible radiation to detect them, they would be hard to see. There are natural materials. We can make natural materials, carbon-rich materials on Earth that are 99.99% reflectant. So they're essentially completely black. And it's possible that organic material or life forms could be that dark. So those are examples of things that would be very hard to detect visibly. More generally, we imagine that life has a metabolism and that life uses energy. And so life's energy usage could be detectable in different ways, for example, by emitting infrared radiation. So typically, in the business of life, life is taking in, for example, in photosynthesis, life is taking in energy with the effective temperature of the sun, thousands of degrees Kelvin, and it's emitting it as heat with an effective temperature of hundreds of degrees. That degradation of energy is typical of life, the emission of heat, if you like. Radiation of heat is a waste product. And so that's a way we would look for dark things, because cool things don't emit light, that could be indicative of life. So there are sort of indirect techniques. Now, beyond biology, of course, there are subatomic particles and components of the universe that we don't yet understand, dark matter being a good example, and those are essentially dark by inference because they don't interact with light in any way. So dark matter is the archetypal example of something that is a big component of the universe that by inference, because of the properties we measure, it only manifests itself by its gravitational effect. It apparently has very weak interactions with electromagnetic radiation of any kind, and so is essentially dark.
Okay, the next question from an email comes from Shay, who asks, hypothetically, if an astronaut would appear to freeze as they get closer to the event horizon of a black hole due to time dilation, could information be recorded in or at the edge of a black hole like a permanent message in a bottle?
Yes, that's an idea that's called the holographic principle that has been around for actually a couple of decades. I think the two physicists that worked on this were Susskind was one of them, and a guy who worked with Stephen Hawking. It's terrible, I'm blanking on his name. But a colleague of Hawking also worked on this idea. So yes, if the information, which is to say the infalling object, their clock appears to go slowly, they also will appear to be highly redshifted. So their radiation as they get close to the event horizon has to escape the gravitational field of the black hole. And in doing so, it suffers a severe gravitational redshift. And so the energy is degraded or stretched to longer wavelengths. And eventually, if you stretch a wave infinitely, of course, it fades to black. So while the clock is slowing down of the infalling object, the radiation that is coming out from them as they fall in is being redshifted essentially to darkness. But logically and extrapolating, that information may indeed then freeze on the event horizon. So hence the holographic principle, the idea that the event horizon is somehow coded as a surface with the information of all the objects that fell towards it asymptotically. It would be an interesting idea to test, and it's certainly a viable proposition, but we have no way of testing it at the moment.
Interesting. And the next question is from Anita, who would like to know if teleportation is possible with quantum entanglement, and can humans be teleported?
Yes. Teleportation, that is the perfect fidelity transmittal of quantum level information, quantum states from point A to point B, has been proven to be possible in practice. The theoretical objection to it, which revolves around the collapse of the wave function in quantum theory, that was actually addressed in a paper in 1995 by Bennett. And so the theoretical objection to teleportation was removed theoretically decades ago. The practical demonstration that you can transmit quantum information with perfect fidelity across a distance has happened steadily but quite impressively in various lab experiments. And they typically involve coherent split photon experiments, where a coherent split photon state is maintained over a distance in the lab. And these experiments now of entanglement essentially have been now carried out on intercontinental scales. And if that information can be maintained across a large distance through an entangled state, then that is the essence of teleportation. And so that has been demonstrated for single atoms, so split photons and single atomic state situations over thousands of kilometers. In terms of multiple atoms, or transmitting the information of more than one atom or one state, that's been done in the lab, I think, for numbers like 20 or 30 atoms across distances probably of centimeters in the lab or meters in the lab. That's not much of a success rate or much of a rate of information transmittal, since the human body contains hundreds of billions of atoms, and so we're talking about a few dozen for teleportation in the lab. So it's a very infant technology, and no one has any idea whether it can be scaled up or not into some substantial macroscopic object being teleported. But it is interesting that in principle it's allowed by the laws of physics.
All right, the next question is from an email sent by Tony, who asks, how is it possible, or is it possible, to have negative mass?
It's a concept in physics that has some validity. For instance, the vacuum of space is able to generate antiparticle-particle pairs from the pure vacuum. And since this is essentially borrowed energy, it's the equivalent of having negative mass of particles and antiparticles, that they come into being and then disappear in a very short amount of time, obeying Heisenberg's uncertainty principle. So that's one area, the sort of virtual particle-antiparticle pairs, a phenomenon that's demonstrated in the lab to be real, that the energy of the vacuum is real and it can generate these particle-antiparticle states. They have the character of negative mass. Otherwise, negative mass doesn't have a conventional meaning in physics, because mass is a positive quantity. Now, energy, of course, can be borrowed, and so the idea of negative energy, potential energy, energy that's borrowed and then given back, this is a pretty standard idea in physics, but it doesn't really map routinely to the idea of negative mass.
The next question is from HZ, who's on with us live, who says, at the present time, there are still some people who believe that the Earth is flat. What is some of the evidence that shows definitively that the Earth is, he says round, but a sphere?
Right. It's interesting. Yes, the flat Earth conspiracy theory or myth, has come and gone over the years. obviously, it was very strong in the medieval and Middle Ages, which is ironic since the Greeks had geometric arguments to show that the Earth was round. And that knowledge sort of went away for hundreds of years in medieval and Middle Age times until modern science started. And it persists as a common myth. I don't know what the percentage of people who believe in it is, probably only a few percent, but a few percent is probably too many. It took a bump. If you look at, you can look at Google Analytics and show, in terms of Google searches, flat Earth searches jumped up, and they bounced around all over the place, but they jumped up substantially a year or so ago when a famous unnamed basketball player, I know who it is, I won't embarrass him further by saying his name again, was quoted on an online video forum as saying, yeah, sure, the Earth is flat, like he believed it, there was no doubt. And then some other sports figures weighed in the same way. Well, sports figures are not known for their science knowledge, so we can maybe give them a break. But of course, by putting this out on the internet to their hundreds of thousands or millions of viewers and followers, it didn't really help the case. It's interesting that there's another variant of this mythology or conspiracy theory, which is the hollow Earth idea, the idea that the Earth is hollow, and so the Earth therefore could be a constructed object by another alien civilization. But just to deal with the round Earth for a minute, or the spherical Earth, the idea that the Earth was a sphere was first in play by people who didn't have telescopes, but who had invented the idea of how objects reflect light in space, and they had the ideas of logic and mathematics, and that's the ancient Greeks. So it was well known in Greek times that in a lunar eclipse, the Earth cast its shadow on the moon. And you can see in a lunar eclipse, the Earth is casting a round shadow. And the only and this was true because lunar eclipses happen fairly frequently, much more frequently than solar eclipses. It didn't matter what the configuration in space was, the Earth always casts a round shadow. And this also shows someone easily that the Earth is bigger than the moon because the arc of that curve is much shallower than the curve of the moon itself. So the only object in 3 dimensions which always casts a round shadow is a sphere. And so the Greeks were uncontroversially aware that the Earth was a spherical object. And then through the famous Eratosthenes experiment, measuring the shadow at midday at one point in Mesopotamia and another point in Egypt, they actually calculated the size of the Earth. So the average Greek knew that the Earth was round or sphere, and they knew what its size was. This information, of course, was lost when the Greek civilization died and the medieval and Middle Ages and Dark Ages set in. The modern era, we still have the Greek argument, still works pretty well, but of course we have much more direct evidence because we've left the Earth. And so perhaps the most iconic photograph almost in the history of the space program was that looking back at the Earth on Christmas Day 1968 from Apollo 8 as it orbited the moon, giving the rise to the notion, 1968, the middle of the environmental movement in the 1960s, of the pale blue dot of the Earth as a fragile, delicate, colored sphere hanging in space. So that's probably as good evidence as you want, unless you're an Apollo denier, and then of course that evidence doesn't mean anything either.
Thank you, Chris. The next question is from John German, who sent an email asking, what are your views of the quantum foam universe idea? There was an article that mentioned that the universe might actually be one of many encased in giant foam-like bubbles. Is there any validity to this?
Well, there's been a theory around actually for a few decades. So as part of the inflation idea, that's the idea that was generated by trying to explain why the universe was so smooth and flat. So the fact that the universe is smooth on large scales and spatially flat has been known for some time. And that's a little bit of a puzzle given that the early universe was dense, curved, knotted, and not flat at all, and not smooth at all, actually, on a small scale. Inflation accomplishes this by stretching out space dramatically in the very first fraction of a second. It's due to some force or field that we don't yet fully understand. Inflation essentially says that the universe was a quantum event. And from the inflationary idea, which emerged from a set of physicists in 1979 and 1980, and a related idea came along quite quickly, which was of eternal inflation. And in eternal inflation, this quantum event that led to our universe was just one of many quantum events. And so you have the multiverse idea or parallel universes or the space-time foam that the question alludes to. They're all related ideas around the fact that the Big Bang, the beginning of our universe, our space-time, is not the only situation that occurred, that there were other parts of this precursor state, which you can call a quantum foam if you like. It's not a bad description, that led to other universes. Not all of them expand. They have different laws of physics. Some are stillborn, and so on and so on. But that's where that idea comes from. It's an untested idea. It's still on the table because it is part of the theoretical framework of inflation, but it's a moment untested. It may be testable, but not tested yet.
Thank you, Chris. The next question is from a live viewer, Matt James, who would like to ask, Jupiter's Great Red Spot has been observed to be shedding and shrinking. What could be causing these changes?
Yeah, the red spot is an interesting atmospheric phenomenon because, of course, we know it's existed for at least 4 centuries since it was spotted as soon as Galileo invented the telescope. So it's an atmospheric phenomenon that is very long-lived. And in fact, if we model, just using lab physics and scale it up, it's completely plausible that a giant planet will have atmospheric features that could persist for centuries or even millennia. But the spot is not unchanging. And in fact, we've seen more dramatic changes in some of the more subtle. Uranus has had spots. All the gas giants have spots or atmospheric features that are notable, dark or bright. And their features have changed even more dramatically than the red spot. But in each case, what's happening is the planet has wind patterns. There's extremely high winds. So all the gas giants have wind speeds of hundreds of miles an hour in banded, layered structures. They also have very thick atmospheres. And there's convection. So there's heat loss. There's heat coming in from the outside. And there's convection inside. And it's essentially the shear patterns plus the convection that's circulating gas from lower in to higher up that generates changes in the overall pattern. So it's long-term stable because it's very large and set up by the wind shear, but it's short-term unstable and variable because of the convection and because of the interfaces between these wind boundaries within the planet, where there are big speed differentials. You can have turbulent effects and changes that affect the shape of the spot. None of this is enough to make the red spot disappear, however. It's a very persistent feature.
All right. The next question is from an email sent in by Gitanjali Rajulal, who asks, how do astronomers measure the size, mass, and age of stars in faraway galaxies?
So in distant galaxies, or even in nearby galaxies, we don't really see individual stars. Especially in distant galaxies, we don't see stars individually at all. The only kind of stars we ever see individually in most distant galaxies are supernovae. That's single massive stars where the brightness of that single dying star can approach the light of the entire galaxy, and so we can study that one dying star. Outside the nearest set of galaxies where we can see variable stars like Cepheid variables and RL Lyrae variables and red giants and blue giants and red supergiants and blue supergiants, the most massive and bright stars, small numbers of them, we don't see individual stars. So for most galaxies, we talk about stellar populations. So astronomers use spectroscopy of patches of the galaxy or the whole galaxy to measure the mean color and spectral features of its stellar populations. And then they make a model of those stellar populations, and they typically reference it to what they know about nearby spiral and elliptical galaxies. And that sort of tells you the mix of stars in any distant galaxy, but it really never tells you about individual stars. We simply don't have that ability to pick out individual stars.
The next question is from Tony Gojanovic, who's on with us live, who asks, is it better to build giant single telescopes or many smaller ones connected together using interferometry? Which is more effective?
And that's an interesting debate, and astronomers covering their bets are trying to do both. Generally, in terms of what the sharpness of your imaging, it's better to spread your surface area, if you like, amongst many telescopes widely separated, because interferometry, your light gathering power will of course just be the sum of all the the surface areas of your individual telescopes, but your resolution in angular sense will be equal to the distance between the widest separation telescopes in your array. So interferometers have the sum of the light gathering power of their various components, but they have much, much better angular resolution. So if it were that choice, you would always go in direction of an interferometer. However, interferometry is a difficult technique to make work. So we have never yet fully realized the potential of interferometry on the Earth, especially optical interferometry. Radio interferometry is very mature. The waves are much less affected by the Earth's atmosphere. That technology has been rolling for over half a century. But optical interferometry is much more difficult. So at the moment, while there are some optical interferometers, and there are individual experiments like the twin Keck telescopes that are designed to be used interferometrically, scaling that up to multiple telescopes is very challenging technically. And so astronomers still tend to want to build the largest single telescope they can.
All right, the next question is from Ann Saffer, who is on with us live, who would like to know if you can help her understand the cosmic microwave background. Where are the measurements taken? Where is WMAP? What's it taking pictures of? And does the WMAP produce the pictures from 13 billion light years away? She's not real clear on how that works.
So the microwave background radiation discovered in 1964 at Bell Labs by Penzias and Wilson, and winning a Nobel Prize some years later for that, they are microwaves, this radiation left over from the Big Bang. So basically, as the infant universe expanded and cooled, there was a point where stable atoms formed, where the electrons could attach to protons and you could have stable material. And that happened at a temperature of about 3,000 Kelvin. So the entire universe, about the temperature of the surface of a cool star, red dwarf. At that temperature, when stable atoms form, photons within the infant hot universe are no longer bouncing around. They are able to travel freely and in straight lines. And so that era, 400,000 years after the Big Bang, when the universe was 1,000 times smaller and 1,000 times cooler than it is now, is the era from which we see this radiation, because that's when it began to travel freely so that we could see a picture of the universe then. You can't see further back because that's like trying to look inside a cloud or a fog bank, because photons don't travel freely. So the microwave background is essentially our image of the universe when it was 400,000 years old. In the intervening time, those what used to be red photons 400,000 years after the Big Bang have stretched 1,000-fold due to the expanding space-time, and they've traveled for 13.8 billion years, and they are now microwaves. And so that was the radiation that Penzias and Wilson saw. And they saw it in every direction in the sky. It was a uniform signal, and that was what marked it out. It was not associated with the Milky Way or with any particular galaxy or star. It was uniform in every direction they looked. The satellites, since their experiment, have just extended the same idea. So COBE launched in 1989, WMAP, which is, I think, around 2000, and then its successor, Planck, actually the most sensitive of these space missions, have put down at the level of 1,000% precision the fact that this microwave radiation is essentially uniform in every direction of the sky. And it makes sense that you'd see it in every direction of the sky because the radiation from the Big Bang fills space. It's all around us. It fills the entire universe. And so naturally, pointing a radio telescope in any direction will see the same radiation left over from the Big Bang. These satellites that did that, WMAP in particular, was at L3, I think, or L4, one of the Lagrange points. So it was situated 1 million kilometers from the Earth to keep it in a radio quiet place. And it was looking around the sky, just mapping the entire sky. And that's the way these telescopes work. And the precision has given us insights into the early universe, but it hasn't changed the underlying features that there's a radiation everywhere in space at a temperature of about 2.76 Kelvin, just a little above absolute zero, that represents relic radiation from the hot Big Bang.
Okay, the next question is from an email. Shay would like to know how scientists measured space-time curvature using the cosmic microwave background radiation, and how did they come to the conclusion that it is flat?
So it's a clever experiment to measure space curvature using microwaves left over from the Big Bang. So as in the previous question, this radiation was released, and the map we see of the sky is referencing back to 400,000 years after the Big Bang. It's essentially looking at almost the entire history of the universe. And it, of course, has traveled for a very long way and a very long time to reach us. So it turns out that there are the speckles or fluctuations in temperature and intensity in the microwave background are not completely random or uniform. There's a characteristic scale of these speckles, some people have called them, that sort of fluctuations. The pattern you see is typically color-coded red and red to blue, where red is slightly cooler and blue is slightly hotter than adjacent regions. The characteristic scale of this is just under a degree, 1 degree on the sky, sort of twice the width of the full moon or the sun. And that's the characteristic size of the speckles. Those characteristic speckles are essentially the seeds for galaxies that would one day form. So basically you have a characteristic angular scale of these speckles in radiation that's seen across the entire history of the universe. And then you make a model for the universe and its expanding space-time and say what should have happened to those speckles, the size of those speckles, depending on the curvature of the universe. And just like a lens and just like optics, if the universe were flat and smooth, then the speckles would not change size. They would start at 1 degree angular scale, and they would stay 1 degree angular scale when you detected the radiation. If, however, the universe had positive curvature, like a convex lens, then those speckles would be magnified, and they would actually have larger angular scale. If the universe had negative curvature, like a saddle in 2 dimensions, those speckles would be demagnified and have smaller angular scale. So by comparing the angular scale seen in the microwaves soon after the Big Bang with a model for what the space would do to those speckles traveling through space and time, you can say whether the universe we live in is flat, positively curved, or negatively curved. And the answer within 1% is that it's flat. It's a very striking result.
Okay, the next question is from one of our live viewers who named Robert Hartman, who would like to know if there are black holes with immense gravity, are there also massive objects with immense repelling power, like a massive ball of dark energy?
That would be an interesting prospect. So yes, dark energy does have since it's causing space-time to expand at an accelerating rate, it does have the characteristic of negative pressure, or anti-gravity, if you like, is a sort of colloquial way of putting it. And that's interesting. If indeed you could harness dark energy, if dark energy were inhomogeneous and there were pockets of dark energy stronger than other parts of space and it varied in time or space, that phenomenon might exist. It turns out that no variation in dark energy has been found with an astronomical measurement. The level of dark energy appears to be independent of space and time. It's uniform. And that, of course, is in accord with Einstein's cosmological constant, the way he originally framed this. It was his attempt to stabilize the universe because he was told the universe was not expanding, and his equations caused either natural expansion or contraction. So he suppressed the expansion with this term, the cosmological constant. So dark energy in our universe does seem to have no structure to it, no features, nothing to hang your hat on to say that it's localized in time or space. So the phenomenon that you're hypothesizing in the question would be very intriguing, but there's no sign that we can search for it.
The next question comes from B, who is on with us live, who asks, who says, "Hi, Professor. I was wondering, why are stars and planets round? Why not some other shape?"
Gravity will tend to form a minimum energy configuration. So gravitational energy, there's gravitational potential energy, which is the tendency for something to want to move under the force of gravity. And since everything will move towards a minimum energy configuration. That's a symmetric configuration. So even if you formed an object that was long and skinny or had some irregular volume, if it had strong enough gravity, it would form itself into a sphere. And of course, the demarcation between planets and asteroids, for example, or dwarf planets and planets, reflects the fact that they have enough material, and the material is not completely solid, it has some suppleness or some viscosity, that they will form a sphere. For stars, which are just made of plasma, high temperature gas, they naturally form a sphere and stay that way their entire history. So spheres are indeed natural configurations for any gravitational situation.
All right, the next question is from Christy, who sent an email asking, are you excited about Hayabusa 2 starting the trip home the asteroid return mission, and is there anything in particular that you are looking forward to?
Well, we get so few samples of the nearby universe. You know, we've had samples from the moon samples, of course, brought back, and we have free samples from lunar meteorites. We have some Martian meteorites, but it's extremely rare to get. It's just a handful of times we've had samples of more distant and primordial solar system material. So at this point, we have so little of these samples to deal with. And of course, OSIRIS-REx here is going to bring back a sample, you know, on behalf of University of Arizona scientists in 5 or 6 years. We have so few samples that each one teaches us an enormous amount. And of course, what we really want to do is know what the primordial solar system was like. These objects are referencing the very pristine primitive conditions. They're also going to tell us the likelihood for life in general, because we'll be able to see what kind of organic material are in these objects. Not that we expect any of these small objects of the solar system to be life-bearing. That would be very implausible. But if we found complex organic materials, that would be a very interesting sign that the ingredients for life were really widespread, or the susceptibility of more complex environments to generate complexity towards biochemistry was quite a likely occurrence. And then there's always anomalies. We may find some anomalies. For instance, the deuterated hydrogen ratio that we found not by samples coming in, but by spectroscopy, has made interesting complications for the idea of where the water on the Earth came from. So everything we learn about the composition of a primitive solar system object has kind of provoked us and taught us something new. So yes, I'm looking forward to those sample returns.
And the last question for today is going to be from one of our live viewers, Robert Hartman, who asks, how is it possible for neutron stars to spin as fast as they do? If it is spinning 600 times a second, how does it not explode or rip apart?
Right. So, you know, stars that spin fast are just showing conservation of angular momentum. So just think of the sun. The sun, obviously, it rotates differentially, so it rotates not uniformly at every latitude, but in the aggregate rotates about once a day. Well, if you collapse the sun by a factor of 1,000 or 100,000, it would spin 100,000 times faster. And so if you do the math, a solar-type star that collapses to the size of about 10 kilometers, something like a neutron star, is going to spin in a tiny fraction of a second. And so we have pulsars, for example, that are millisecond pulsars that spin hundreds of times a second. Because they are extremely dense and made of essentially neutron material, they retain their structural integrity, because it's just like an atomic nucleus with an atomic weight of 10 to the 57th. That's what a neutron star really is. There are small shifts and seismic rearrangements of that neutron material. They're called neutron star quakes, and they've actually been observed in pulsars where the frequency of the pulsar sort of shimmies or changes slightly, but they will not blow apart or fall apart because it's essentially like, as I said, a big atomic nucleus. So it has structural integrity of the atomic nucleus that it is. And the speed of rotation is simply a consequence of that enormous collapse from a larger object spinning much more slowly. So thanks for that question, and thanks for all your questions today. They were good as always. Thanksgiving's coming up in the next few weeks. We'll maybe try and get one in just before Thanksgiving. So thanks for your questions, and until next time.